Hello, my name is Evie, and I'm a second-year engineering student studying creative technology and design at the University of Colorado Boulder. Today's lesson is all about machine learning, and I have HelperBot here, who runs on a machine learning model, to help out. I'm sure everyone has heard of machine learning at least once in today's world. And if not machine learning, you've definitely heard of artificial intelligence, shortened to AI. AI is a program that can adapt based on information it receives. It's a general definition, while machine learning is more specific. Machine learning is a subset of AI, where algorithms improve as they're exposed to more data. Then there's deep learning, which is essentially machine learning, but with many more networks within it and vast amounts of data it learns from. Today, though, we're going to learn the very basics of logic a machine learning model may use. It's actually quite similar to how we make decisions ourselves. We tend to make a lot of decisions based on information we receive from the surrounding environment. We take in information, process what it means, then do an action based on that information. For example, we can take in the information that it is 40 degrees Fahrenheit outside. We then go through the process of if we should wear a jacket or not. If it's above 60 degrees, we don't wear a jacket, but if it's below, then we do. We end up taking the action of wearing a jacket because the information we gathered earlier was that 40 degrees is below 60, which means it's chilly enough for a jacket. Now this is more simplified than what actually goes on in our brain with neurons firing and all, but the concept is important. An artificial neural network, or ANN for short, is modeled after the human brain. It uses the simplified concept I mentioned earlier. It follows a similar idea of how we make decisions by getting an input signal, processing it, then acting on it. It essentially turns an input into an output. For example, it could be asked if a number is greater than or less than 5. If we receive the value of 4, then the algorithm takes the action of returning that 4 is less than 5. Let us walk through some basic logic functions. These are very common and can be used in many scenarios. Typically, we use ones and zeros with these functions. 0 usually means false, and 1 usually means true. These are called Boolean data types, and are very commonly used in code or logic functions. We also typically use set notation to convey this information. For example, this means that y is an element of the set 0, 1. In simpler terms, it means that y can be either 0 or 1. For the first function, we have the OR function. This function means that if either condition is true, then the output is true, or 1. For example, if x1 has a value of 1 and x2 has a value of 0, then the output, or y, would be 1. It results in a 1, or true, because at least one element in the set of values is equal to true as well, and it only has to be one or the other. Here's a table that might help out a bit as well. It's read left to right. It gives us all the possible outcomes with two values that can be true or false. If x1 is 0 and x2 is 0 as well, then the output would also be 0. Even added up, they're still false. Meanwhile, if x1 is 1 and x2 is 0, then the output would be 1. It would still be true added up as well, because only one of them needs to be true for the output to be true. The rest of the table isn't filled out though. Can you fill out the rest of it? Pause the video if you want to try it yourself. Right, 1 plus 1 equals 2, which still equals an output of true. Then the last set of elements are the same as the previous one with x1 and x2, simply switched, so that is true as well. OR statements typically mean that if any input is true, then the output will be true as well. For the second function, we have the AND function. This essentially means that both x1 and x2 have to be true in order for the output to be true. Here's another table. There's more spaces blank this time, but I think you can fill it out. Pause the video if you'd like to try. Did you notice that there's only one true output in this case? That's because in an AND function, both inputs have to be true for the output to be true, so the rest will be false. Last but not least, we have the XOR function. This means that in order for y, or the output, to be true, x1 or x2 have to be true, but they can't both be true. Another way to say this is that they're mutually exclusive. Let's see if you can fill out a table all on your own this time. Feel free to pause the video to do so. Good job! Notice how there's only two true outputs this time. A XOR function essentially means that one or the other can be true, but not both. It creates a threshold of 1, where x1 plus x2 has to be equal to 1, otherwise it isn't true. These are all the basic logic functions that an artificial neural network may have. A more complicated machine learning model may have hundreds or thousands of logic systems like this to make up something more sophisticated, just like how the human brain has lots and lots of neurons as well. This is called a perceptron model. It utilizes the functions we just discussed in a visual manner, like this. We can now also add weights and a threshold to each input with this model. For example, here we have 3 inputs. x2 and x3 both have a weight of 0.25, while x1 has a weight of 0.75. We also have a threshold to test the weights. For example, we can test if x1, x2, and x3 are true or not. We get 0.75 times 1 and 0.25 times 0 twice, which is equal to 0.75. 0.75 is greater than our threshold of 0.5, so we get an output of 1, or true. A key limitation of the single-layer perceptron is that it can only solve problems that are linearly separable, like the OR and the AND functions we discussed. This means it cannot learn some functions, like the XOR function, which cannot be separated by a single line. To overcome this, engineers use multi-layer perceptrons. These models have multiple layers of perceptrons, and they use special functions called sigmoid functions to allow the model to learn more complex patterns that single perceptrons cannot. Machine learning uses perceptron models with weights to learn. It first uses the training data to get a set of inputs and randomly picks weights for all the inputs. It then compares the output of the model to the actual output of the training data. If it's correct, it does nothing. If it's incorrect, it calculates the error and adjusts the weights for the next input so it can match the output correctly. It repeats this and keeps making adjustments until the model is able to accurately predict outputs. This can be used for calculating when a car's parts may fail, or what shows people most enjoy so a streaming service like Netflix can understand what their audience likes, or how to improve diagnoses and treatments for healthcare professionals, or more. You could even use it to decide if you want to go to a football game or not, instead of a model like this. This model says that if any 2 of the conditions are met, then you would go to the game. Now you know the basics of machine learning. We only scratched the surface, though, as machine learning can get much more complicated than these functions. Think about the human brain. We have billions of neurons that all receive different inputs and return different outputs. Trying to translate that into a machine takes billions of functions and formulas as well in order to mimic a human's brain, so you can imagine how complicated it can get. HB here has a pretty complicated artificial neural network too. It's enough to make them sentient, pretty much, so it's all packed in there pretty tight. I encourage you to see how your decisions can fit into a perceptron model, or how you can solve problems with one. It's a pretty useful model to know, especially in today's day, where technology is incredibly prominent. Anyways, that's all for today. Thanks for watching, and we'll see you next time. Check out the full lesson on the TeachEngineering website. Then, check your knowledge of machine learning by using a NetLogo platform to run simulations of a basic neural network in Computer Simulation of an Artificial Neural Network.